There we go. So this is, let's continue then with this lecture on digital geometry and mathematical morphology. Yeah, so sorry about the mistake in the slide before the breaks. This is the way the masks should look like. It's also updated in Studium if you download the PDF from there. And I'm sharing the screen, yes. And the raster scanning, the process is just in this small mask to propagate the local distances and put this mask at new positions. So row by row is scanned like this, row by row and then column by column. And eventually we get to the final result. We do a forward scan and a backward scan. So this is what we get. And now each pixel is labeled with a distance to the closest background pixel. If I didn't make any mistakes in this example. So let's pick one at random. I don't know, this 10, for example. Which background pixel is the closest? Well, in this case, it's actually this one. So then the shortest path would be the path going like this. And the length of that is first is 3-step, then a 3-step, that's 6, and then a diagonal step, so that's 10. All right, so that's 2 ways to compute the distance transform. So these are with weighted distances in a kind of digital geometry approach. Similar methods can be used for the Euclidean distance. But I will not go into detail about that. What you could do is to propagate vectors instead, so you get the vector to the closest background grid point. But there are some things to consider. Then it's a bit more complicated. Yeah, also for Euclidean distance. All right. So what about applications then of distance transforms? We can do constrained distance transform to get to kind of find the shortest path, path planning approach. So a constrained distance transform, that's when you have pixels in the image that are not allowed to cross by the paths, the shortest paths. And that can be used for navigation and I don't know, in this sketch image here to sketch figure to find the shortest path between 2 points in a room. Or it can also be used to find distance transforms of curve patterns or line patterns like this. So the distance between 2 red dots when you're only allowed to stay within this black region, for example. So what you can use then is a constrained distance transform. And this is an example of that. So we have a seed point, a start point. And then we compute the distance transform, and the distance transform will be computed as the shortest path between the seed pixel, start pixel, and any other pixel in this image where the blue pixels are not allowed to pass. So to get from the seed pixel to this point, for example, what you need to do is you need to go this way, and follow this path to get to this position. And then when you have this distance transform and you want to find the shortest distance between the, or the shortest path, I should say, between the start point and any point or pixel in this image, what you can do then is to just follow the steepest slope back to the starting point. And if we look at an illustration like this, where the height of the pixels correspond to the distance value. So here we have a seed point somewhere around here. And then if we start at a pixel around here, so that would correspond to position around in this region of this image. So that corresponds to this region of this kind of landscape image. So what you do is you just find the steepest slope in the distance values back to the start point, and that way you get the shortest path. Right, and this is how it's actually computed as an example in another image. So we have a start point and an end point, and then to find the shortest path back, we just find the direction with the largest slope. I wanted to talk a bit about matching. So this will lead up to something called chamfer matching, which is quite an efficient method that can be used for matching a certain shape in an image. And this will be used in one of the computer exercises, Natasha said. So matching, that's used to locate known objects in an image, to search for specific patterns, etc. It can be used for registration, to align two images, matching of car number plates, for example. There are several different applications for this. There are different approaches to do matching. We can use image pixel values directly, correlation methods. We can find low-level features such as edges and corners, or high-level features, relations between features, or identified parts of objects, or so. What we will work on is somewhere between the first two, actually, or it will be based on edges, but mainly pixel values directly. I'll show what we'll do. So this is the chamfer matching that I wanted to talk about. So this is based on distance transform, and it's used to locate one-dimensional features or edges. Yeah, so good response in close to correct positions, but poor elsewhere. So this means that the initialization is very important. I'll show examples. So generalized distance is defined, and then you move the template in a way that you get as close as possible to what you want. So I think an example is better. So this is, in this example, we have an image with some different numbers like this, 4, 7, 8, and 9, and then we want to find this number 4. What we do then is, for both the templates, so this image of the number 4, and for the original image, is that we do an edge detection thing. So we find the edge image. We compute the distance transform from this edge image. Then we get something like this. And then we place the template in the image, and we search for a position which gives the minimum sum of distance values when we add the distance values under the edge image of this template. Yeah, so input to this image is a search image and the template image. So in the previous example, this is the search image, and this 4 is the template image. And output will be an image with the templates overlaid on the best matching positions. Start position, or the initialization, how we start this, is to place the template at different positions in the image, some kind of random covering. Or we can use some a priori knowledge if we know about where the template is supposed to be. And as I said, we extract edges in both the search image and the template image. We compute the distance transform of the search image, so that's this step. And then we superimpose the edge template on the distance transform image. And then we can do rotations, translations, and scalings of this template image. Yeah, so okay, so I saw this question in the chat now, but I think what I just said answered that. So we can consider rotations, translations, and scalings, and also other like sharing operations and so And then for each position of the template, we can compute the root mean square value or error for the pixels that the edges hit. And this gives this generalized edge distance. We can optimize by small steps in the directions of lower edge distances. So if we look at a very close up of a template position here, we have in this image, this is the distance transform image of the search image, so the distance transform. We have these gray pixels, that's where we have the template edges overlaid. And then we do the root mean square computation of all these pixels. This gives the value 1.85. And then we also compute the root mean square for if we move one step to the right, then we get the value 1.07, one step to the left. If we move the whole template one step to the left, then we get a higher root mean square. So by looking in different neighboring kind of positions of the template, we can get the best local step to move the template. And a similar approach can of course be done for other parameters if we have rotation or scaling or so. Right, and here's another example of the transfer matching. The search image, the template image. Here is the template edges. And then when we have applied the transfer matching, this is the result we get. The 6 lowest or 6 best matches. One of them matches exactly, so this was the right leaf in this, the right position for these leaves. Let's see, this was the next best, and so on. So transfer matching can be very useful as a matching technique. Let's move on to skeletonization. So this is the digital topology, if you like, but it will have several flavors of digital geometry. We will use some distance transforms, etc. So skeletonization, that's kind of based on a medial axis transform idea. So this is a thin centered representation of an object. And so the medial axis is often described as the locus of local maxima on a distance map. And I'll show what that means. So essentially, a medial axis, that will be the centered, thin representation of an object. And we will have a look at different ways to attack this problem, or how to generate medial axis. There are several applications. Here are some of those application areas. Object description, object recognition. If you want to describe different objects, if you want to recognize them in different ways. If you want to do navigation in narrow passages, for example, we can find a center line. Animation, to simplify objects and just have a center line and animate that. And different applications have different requirements. On the medial axis representation. So object description and object recognition, then it's often important that the object should be fully described by the representation. In navigation and animation, only the most important features are needed typically. We'll talk a bit about topology. So intuitively, this is the description of an object, of an image, that is invariant under the rubber sheet transformation. So if we stretch the image or the objects in different ways, the topology doesn't change. And this is so topologically equivalent. That's the term that we will use. For those who are interested, I can talk a bit more in detail about difference between homotopic and homeomorphic and so on. But what we'll say here is it's topologically equivalent. And essentially that means that the number of objects, connected components, and the number of holes do not change by this function or this by doing these functions. So one way to describe the topology of an image is by the homotopy tree. And this is now this goes back to the connected components that we talked about during the first hour. So this is an object. Now the background is black. Well, sometimes it is like that, and sometimes the background is white. Here the background is black. And then we have connected components within this image. So we have x1, that's a connected component here. x1 prime, that's a connected component here. And the x1 prime in itself have different holes, x2 and x2 prime. And x2 prime contains connected components. So in this way, we get this homotopy tree. And the topology, if the homotopy tree is equivalent, then we say that the topology is equivalent here. It's a bit of hand waving, but let's accept that for now. So with these examples, we can see that the homotopy tree of the image to the left equals that of the image in the middle here. And that means that the topology of these two images are equivalent. And that also kind of can be explained with this rubber sheet transform. So we can stretch this image in different ways to get this image. So we can stretch this to get it over here and stretch the background so it's a bit smaller and stretch this whole object so that it gets this shape. But we can't stretch this image to look like this. So this has a different homotopy tree, so it has a different topology. Right, so medial axis representations in digital images. So this can be done in different ways. For example, we can use centers of maximal balls, homotopic thinning keeping the centers of maximal balls or disks, or template matching. And different approaches give different properties of the medial axis. Let's see, let's start with the centers of maximal balls, or centers of maximal disks. So now we'll get back to this image that I showed before and explain that in a bit more detail. So a maximal ball or maximal disk is the disk in the object that is not covered by any other disk in that object. So if we look at this, for example, for any other disk within this object, it will not cover this disk. So that means that it's maximal. If we would have a smaller disk around this point here, for example, then there are disks within this object that completely covers that disk. So then it would not be a maximal disk. And the CMB, the center of that disk, is its center. And this all depends on the distance function that we use. Remember, we talked about the chessboard and city block distances and the weighted distances. So depending on which distance function we use, we will get different appearance of this medial axis representation by CMBs. And then the quench function is the function that associates the radius to each of these disks. So that's actually the distance transform value at the center point. That would be the radius of this disk, right? The distance to the closest background point is equal to the radius of this maximal disk. Pixels as centers of balls. So let's look at this tiny example image with a chessboard distance. So now only horizontal and vertical steps are allowed. No, sorry, and also diagonal steps. So horizontal, vertical, and diagonal steps. This is the distance transform that we get. And then if we want to find the centers of maximal balls in this one, we can do that as finding the local maxima in this distance transform. So these pixels that are with red dots here, those are the local maxima in the distance transform, meaning that they don't have any neighbors that have higher distance value than themselves. So this holds for all of these with the red dots, and it doesn't hold for the other pixels in this object. And we can see that these are also the maximal disks or maximal balls in this image. So if we look at the disk that corresponds to the distance value 2 here, it will be this 3 by 3 disk like this. And we can see that there is no other disk with this shape within the object that completely covers this disk. So therefore it's a maximal disk or maximal ball. And if we have this information where the maximal disks are, and we keep the distance transform values there, we can see that this is actually enough to completely recover the object. So if you take the union of all these maximal disks, it will equal the actual object that we had to start with. So if you take the union of this one and this maximal disk and this maximal disk, etc., it will be the exact object that we had to start with. Here we can see asymptotic shapes or the shapes of disks with different metrics or different distance functions. So this is a city block, this is a chessboard, this is 3-4 weighted, and this is Euclidean. And we can see that the Euclidean has lower rotational dependency. The 3-4 weighted has a bit higher rotational dependency, and the chessboard and city block, they are just essentially squares. City block is a tilted square, but they have very high rotational dependency. So this is also for weighted distances, the centers of maximal balls are the local maxima in the distance transform. What we need to do then is to take the weights, the local weights, into consideration. So to check if a pixel, if its distance value is a local maximum or not, we need to know what are the weights in this weighted distance. Right, so the sets of centers of maximal balls look different depending on which distance function is used. So we have the city block distance. So this is an image that we will use to compare these different approaches. Background white, object black in this case. These are the CMBs when we use city block. These are the CMBs when we use chessboard, and these are the CMBs for the 3-4 weighted. What we can note here is that the topology has changed, of course. The number of connected components, there is a huge number of connected components in this example, but for the original image, it was just one connected component. So this does not preserve topology, and I'll get back to that. And here we can see that the union of all these disks actually equals the original object. So these are the maximal disks of different radii. So this is with radius 1. When we use city block distance, this is radius 2, radius 3, etc. Right, and this also says that we get a complete description by the CMBs. So with this object, we have the CMBs, those in black, and then from these CMBs and their distance value, we can compute something called the reverse distance transform to get the original object back. Yeah, and this is how it's actually done. So we have, so instead of adding local weights, we subtract the local weights from the CMBs and their distance values. Let's not get into details about that. Right, I want to mention simple points. So this is thinning, the process of obtaining a medial axis or a skeleton, homotopic thinning, and we're using simple points. And simple points or simple pixels are those that can be removed without altering the topology. So here are some examples. The central pixels are considered here. So this one to the left is not simple. So if we remove this central pixel, the number of connected components in this image will either go from 3 to 2 if we use 4 connectedness, or it will go, if you use 8 connectedness, this is 1 connected component, and if we remove the central one, it will be 2 connected components. So this is not simple. Removing that pixel alters the topology. This example, then we have a simple pixel. So the number of object components and background components, number of holes, etc., will not change by removing this one. And for the ones to the right, well, this actually depends if you use 4 or 8 connectedness, if they are simple or not. This holds for this and this one. So homotopic thinning, the idea is to remove border after border of the object if the pixel is simple. So we remove non-simple pixels. No, I'm sorry. We remove simple pixels border after border until no more pixels can be removed, or if we meet some other criterion. And the number of iterations, of course, depends on thickness. So this is actually the algorithm. Find border pixels, remove border pixels if they are simple. Or we can use the distance transform to define borders in the objects. So if you use this running example, this toy example, the original image, if we iteratively remove simple points or simple pixels, eventually we will get to this result. And now we can see that if we use 8 connectedness for the object and 4 connectedness for the background, that's what has been used here. We can see that the number of object components is 1 in the original image, and we can see that it's actually 1 also in the resulting medial axis representation or skeleton. So this actually preserves topology. The number of holes is 1, 2, 3, and the number of holes is 3 also in this medial axis representation. Then we can do a very similar thing, but we can keep the centers of maximal balls. And the reason why we do that is that if we have the CMBs, the centers of maximal balls, remember, then we can get the original object back. And that can be a feature that we want our medial axis to actually have. So what we do then is we compute the distance transform, we find the CMBs, and now we remove border after border if the pixel is not a CMB, but if it's simple. So we remove simple pixels that are not CMBs iteratively. And again, the number of iterations depends on the object thickness. And this is a result we get in that case. So the original image, if you use the city block distance, we get this result. The chessboard distance, we get this result. And the 3-4 weighted, we get this result. So these are homotopic representations, so topology preserving representations. So they have the same topology, the same number of object components, and the same number of holes. But in this case, we can actually get the original object back since we have all the CMBs, which is sufficient for that. And here we can see this process in an object. So this is white background, black object. And this is what happens. We remove border after border if they are simple, if they don't change the topology, and if they are not CMBs. So here we start to keep the CMBs as anchor points. And we can see that these protrusions start to shape. And border after border until we have this medial axis representation. And here we can see result of homotopic thinning, keeping the CMBs with different distance transforms or distance functions. So this is city block, this is chessboard, this is the 3-4 weighted, and we can also use the Euclidean distance. And this boils down to different aspects. Shape preservation, is that of interest for us? Should we use it for compression? Is it important that it's stable under rotation, that we have low rotational dependency, etc.? And then the last thing that I wanted to mention is thinning by morphology or by using a template. So then this is an application of hit or miss. Where we have structuring elements for object and structuring elements for background, and we check if this template fits the object and background in a hit or miss approach. So what we do then is we identify border pixels. We can use the distance transform for that, for example. We can remove pixels satisfying the structuring element. And then we have a composite structuring element again, object, background, and here it's also don't care pixels, but that just depends on how you formulate this. So in this case, we have the ones should be in the object, the zeros should be in the background, and then these asterisks are don't care pixels. And we do these and all the kind of obvious rotations of these. And this is the result we get. It's very similar to homotopic thinning by simple points. All right, so these are actually medial axis representations, and then I've been talking about skeletons. And so what's the difference between medial axis and skeletons? Well, there are some properties that relate to if a medial axis is a skeleton or not. So what we want a skeleton to be is that it should be topologically equivalent to the object. It should be centered within the object. It should be unit wide, and it should be possible to recover the original object by some kind of reverse operation. And sometimes a skeleton is defined as a transformation having all these properties, and sometimes that is a bit relaxed. And as we can see with the approaches that we have brought up today, the set of CMBs, centers of maximal balls, it's not topologically equivalent to the original object. It is centered in some sense. It's not unit wide, but we can get the original object back by a reverse operation. Homotopic thinning, it's topologically equivalent, it's centered, it's unit wide, but we cannot get the original object back. Homotopic thinning, by keeping the CMBs, it is topologically equivalent, it is centered, it's not unit wide, but we can get the original object by reverse operation. And then thinning by template matching, then we have the same properties as for homotopic thinning with simple points. All right, so I have actually talked about quite a lot of different things. Some of this will appear also in computer exercises that you will see eventually. During the first hour, we talked about morphology, erosion, dilation, opening, closing, hit or miss transform, different properties of that. There is a section in the book about this. Let's see. So I suggest that you read that and look at the examples and read how how this can be explained in a different way. There is also a section about distance transforms that you can read to get some additional understanding of what I've talked about. Connected components, we talked about that too today. So you can read that in the book. Right, so after the morphology, we talked about digital geometry and the kind of general concept of digital geometry. What is that all about? And then we moved on to distance functions and distance transforms and applications of distance functions and distance transforms, including finding shortest paths in kind of path planning applications, and also skeletonization, medial axis transform, which is kind of digital topology rather than digital geometry. But since we also have the distance functions and distance transforms, there is a clear link between digital geometry and digital topology. Okay. So that's what I had prepared. Do you have any questions that you want to bring up now? I'm of course also available on email if you have questions also later. All right, but otherwise I'll say thank you so much for listening and being active. Feel free to come back to me if you have questions, and don't hesitate to do so. And I'm always available for answering questions. Okay, thank you all. Take care. Bye.